Okay, after discussing about mean and variance of Poisson distribution, there are certain things about Poisson distribution which you ought to know. There's something called recurrence relation. Recurrence relation for Poisson distribution. For Poisson distribution. What that is just writing, all of us know recurrence relation is like to find the n plus 1 term. You'll be putting it in terms of nth term. For certain things, it can be a set of nth terms, nth term, n minus 1th term, like that. Okay. So we all know what is the P of R, P of X is equal to R for Poisson distribution from the previous videos. E power minus lambda, lambda power R by R factor. What would be P of R plus 1? How will P of R plus 1, P of R plus 1 be is e power minus lambda, lambda power R plus 1, e power minus lambda, lambda power R plus 1 by R plus 1 factorial. I'll just rewrite it, that's it. Okay, so lambda power R plus 1, I'll take lambda out. Okay, in R plus 1 factorial, I will take R plus 1 out. So it will be something like e power minus lambda, lambda power R by R factorial. Done now? Right. This is nothing but P of R or P of X is equal to R. This would be called P of R, guys. And this would be called P of R plus 1. Shorthand notation, that's it. Because all the time it's difficult to write. Okay, so it is nothing but lambda by R plus 1 into P of R. P of R plus 1 is equal to, this is the recurrence relation. Using this, if you know the previous probabilities, you can calculate the successive predecessor probabilities. If you know, you can calculate the successive probabilities. That's the motive behind recurrence relation for Poisson distribution. Next, there's one more thing which you ought to know. The moment generating function for Poisson distribution. Before going to that, we'll talk about the general definition. We'll see first the general definition, because once you know the definitions, the concepts will be clear. What that is there's something called moment generating function. Those who have done this course on statistics, they'll be knowing what moments are. Okay, what are moments? First moment would be mean in a certain case. Okay, second moment will represent variance in a certain format. Third moment will represent skewness and kurtosis. Because while calculating all the moments, the mean, variance, skewness, and kurtosis, while calculating these measures of central tendency and dispersion, I'll be using all the moments. Okay, especially the first four moments we'll be discussing or we'll be using in the formulae for skewness and kurtosis as well, along with mean and variance. So I should know what exactly generates these moments. There's a general formula for moment generating function, mx of t. It's denoted by mx of t. It is nothing but expectation of e power tx. Okay, expectation of x is mean of x. Expectation of e power tx is moment generating function. Moment, it is not moments generating, moment generating function. Of course, this expectation term would be summation e power tx p of x. For discrete, it would be integration e power tx p of x dx for continuous. For continuous variable and for discrete variable. For discrete random variable, it is summation. For continuous random variable, it is integration. That's it. From minus infinite to plus infinite. By the way, it's a definite integral. From minus infinite to plus infinite. This is the definition for moment generating function. What I ought to remember is that expectation of e power tx is moment generating function. Okay, now coming to the moment generating function of Poisson distribution, using this definition, I'll be proceeding with the Poisson distribution moment generating function. Okay, moment MGF. In short, it is called, all the time it's difficult to write the full form. So I'll be calling it MGF of Poisson distribution. MGF, CGF, MGF. Cumulant generating function, moment generating function. Okay, let's see first MGF, then We'll get back to CGF as well. We'll get to, since Poisson distribution is a discrete distribution, na? Poisson and binomial are discrete because you have finite number. When there is an infinite number, that too, especially in a interval, you can say Poisson, you are taking summation limits from 0 to infinite, 1 to infinite, no ma'am, you can say, but then even then they are discrete. I mean, you can count them countably finite. They are countably infinite is when you have the values of the random variable in an interval a comma b. How many values will be there? Infinite number of values will be there in every subinterval. Okay. So discrete distributions are Poisson distribution. Of course, binomial distribution is out of the box, but without knowing binomial, it's incomplete to discuss Poisson. Anyways, since it is discrete, I'll go with the summation definition of MGF. Okay, E par Tx. P of x or P of r. If this is x here also I will take it. Otherwise I will take r. Anything is fine. Okay. Where x is ranging from 0 to infinite. Right. Summation e power tx. What is P of x for Poisson? I know. E power lambda. Lambda power minus x. I'm sorry. E power minus lambda. Lambda power x. Okay. Ulta I have written. I'm sorry. E power minus lambda, lambda power x by x factorial. If it is x, I'm taking it as x factorial. Yeah. So, just see here. I'll be expanding x is equal to 0 to infinite and see what happens. Okay, e power minus lambda has nothing to do with it. So, I can pull out e power minus lambda and go with the remaining things. What I'll get, just see here. X is equal to 0. When x is equal to 0, I'll be having everything to be power 0, so it is 1. Okay. Next, I'll be having what? Lambda power 1 into e power t by 1 factorial, right? Plus lambda power 2 into e power 2t. I can write it as lambda into e power t whole squared by 2 factorial. Yes. And lambda power 3 e power 3t. I can write like this by 3 factorial and so on. I can clearly see again in the previous video we have discussed the expansion for e power x. It is what? 1 plus x is plus x square by 2 factorial x cube by 3 factorial on and on. So what would be this term? This term is nothing but in the place of x, I have lambda e power t. Okay. So e power minus lambda into e power, see carefully. I have a lambda, I have e power t, guys. Okay. Or I can club both of them because the bases are same. I can add the exponents. So e power lambda e power t minus lambda. Okay. So if I take out lambda common, then I'll be having e power t minus 1. Yeah, I can do other things as well. But as of now, the moment generating function for Poisson distribution is this. Let me write it. E exponent e of course, it's denoted by mxt. M suffix capital X into t, this is equal to e power lambda like this. This is the one. Now, how do I find the cumulants? How do I find the cumulants? It's very simple. Again, you ought to know the definition for CGF. Cumulant. Why you ought to know about cumulants? I will talk about it. Cumulant generating function. Why? Because if I know the cumulants, I need not find mean and variance, guys. That's the shortcut. Okay, cumulant generating function. Let me write the definition for it, then talk about Poisson's cumulative. It's CGF. Okay. In short, it is CGF. These are important for the exam. You can be asked to derive as well. What is cumulant generating function? It's denoted by K, guys. Kx of t. This is nothing but log of mxt. Log of moment generating function is cumulant generating function. Now apply log for the cumulant generating function of binomial. See what happens. Log e base e will give me what? 1. Okay, so lambda e power t minus 1 is what I have. Okay, expand lambda into e power t expansion. I know 1 plus t squared by 2 factorial. T usually you'll have factorial of, it's different. Okay, don't worry, it's factorial always for e power x. Okay, there's a -1 as well, guys. Okay, so this +1 and -1 gets cancelled off. Lambda into t plus t squared by 2 factorial, t cube by 3 factorial plus t power 4 by 4 factorial and so on. It goes on. I'll talk about why this cumulant generating function is needed. What's the basic idea behind finding cumulant generating function? I'll talk about in next video because it's becoming long.